objective of this video is to find the member capacity of the beam. So check the adequacy for the flexural strength of the 460 UB 67.1 bent about its strong axis. All the load applied to the top flange of the beam. The beam is partially restrained at the ends. So beam is partially restrained at the ends, where the lateral deflection are effectively prevented and twist rotation are partially suppressed. The restraint is available only at its end. So there is only restraint available here, not here. The load P star is due to the dead and live load and is applied to the top flange of the beam. So this P star is due to the live load and the dead load, and that value is given 50 kilonewtons. And this W star is the self weight of the beam, which is 67.1, and that self weight is a dead load that is uniformly distributed. Now in this example, the structure analysis will be given to you. Like this is the bending moment diagram. We can find the bending moment at here 106.4 at the middle, and we can also find at the quarter point, like from 2000 millimeters we have 54.5, and it's a symmetric. So around here 6000 millimeter from here we have a 54.8 kilonewton meter. So that's structure analysis will be given to you in the questions. Structure analysis we done it in the previously, so it's not requirement here to do the bending moment diagram for the given case. Now to start with, we are working on the loads. Loads W star is equal to 1.2 times 0.671, and this W star is talking about just the dead load 67.1. so that 67.1 is the self weight of the beam is equal to 0.8. Now this 1.2 is coming from the AS and ZS 117 0.0, and if you have a only strength one and the live load is 0, so 1.2 G. So 1.2 G. So that's what coming from here, close 4.2.2 and 1.2 G. So it's actually here. This one W star is equal to 1.2 G. Now this 0.671 is the 0.671 is 460 UB 67.1, and that 67.1 has a kg per meters. In this case we can convert this 67.1 kg per meter into Newton by multiplying 10. So that's give us 671 kilonewton per meters, and converting into kilonewton per meters divided by 1000 give us 0.671 kilonewton per meters. Substitute that 0.671 in these equations, 1.2 G, it give us 0.8 kilonewton per meter, which is the UDL load of the weight of the beam. Now structure analysis given in the question, so we can draw the bending moment diagram and find a bending moment for these cases, and we know this one is 8000 millimeters. So in the middle 4000 millimeters at here, this is a quarter point, so 2000 millimeters and 6000 millimeters. Because of the symmetry we get 54.8 kilonewton meters. Now section capacity is MS is equal to ZEFY, as 460 UB 67.1 is a compact section, so ZE equal to SX. Now this checking of the compact sections is given in the previous video, so you can check how to prove how do we know whether it is a compact or non-compact. Now ZE, this equations is taken from Australian Standard. On page number 50, clause 5.2.1 is the nominal section moment capacity, MS is equal to Fy ZE. Now to find the ZE for the compact sections, on page number 51 we have a compact sections which has a ZE value of minimum of 1.5 Z and S, but in the case of compact sections we have minimum S, so that S we going to multiply. Now this SX is 1480, which is ZE times 10 to the power 3, is taken from one steel table, 460 UB 67.1, and about the x axis we have an XX value 1480 times 10 to the power 3 millimeter cube. So that is 1480 10 to the power 3 millimeter cube times the yield strength. If you turn the page over on page number 15, 460 UB 67.1, we have a two different yield strength is given, but we should use the minimum yield strength 300 and 320. So the minimum yield strength is 300 megapascals. So that is 300 megapascals. Multiplication gives Newton millimeters, and divided by 1000 and divided by 1000 two times to give us kilonewton meters. So that's section moment capacity is 444 kilonewton meters. Now check if it is fully braced. Now there are conditions here that if L over Ry is equal to less than 80 plus 50 beta m 250 over Fy, in this case we have need to, if this condition satisfy, we need to find the section capacity and we stop there. But if this value is greater than this one, then we need to find a member capacity. So for example, if LAH less than RH, we just find the section moment capacity, right? And if LHS greater than RHS, we need to find a member moment capacity. So it's a quick check for all the bending cases. We generally do these quick checks to see whether we should find the section moment capacity or member moment capacity, and the section moment capacity considered as a fully braced conditions. Now these equations coming from Australian Standard on page number 53 on clause 5.3.2.4, we have L over Ry less than. So once we get these equations, we can find the left hand side. L over Ry, Al is 8000 millimeters, that is given in the questions. That is 8000 millimeters given in the questions. Over Ry is taken from the, that is radius of gyration, that is given from the one steel table on page number 40, 460 UB 67.1, and the Ry value is 41.2, which is given here millimeters. So that is 194 on left hand side. Now right hand side, 80 plus 50 beta m square root 250 over Fy. So if you substitute this value here, 80 plus 50, now beta m is minus 0.8 times 250 over 300. We show you how to find Fy 300. Now minus 0.8 is given on the page number 54 on the Australian Standard, where beta m value is minus 0.8 for segment with transverse loads. So if you compare this 194 and 36, so 194, which is left hand side, is greater than right hand side. So as I mentioned, if it is greater than, we need to find a member moment capacity. So member moment capacity is also flexure capacity. First, the moment modification factors. The alpha m equation is given here. Now that equation is taken from page number 59, where we have alpha m 1.7, so that should be less than 2.5, this big equation that I copied here. Now in here we need to use the bending moment diagram to extract these 4m values. Now in the bending moment diagram, this m star m is written here. M star m is the maximum design bending moment in the segments. So maximum from the bending moment diagram, that is the maximum design bending moment, that is 106.4. M2 star, M3 star and F4 stars. So that is given here, M2 and M4 design bending moment at the quarter point of the segments. So M2, that is M2 and that is M2 star, that is M4 star, and that is MM star. So in here this is a quarter point bending moment, so M2 and M4, so that is 54.8 square, that is taken from here. 106.4, which is also these values, which is written here. Design bending moment at the midpoint of the segment, so that's midpoint also same as this one. So M3 star, so which is 106.4 and times 54.8 square. The calculations give 1.37. Check whether it's less than 2.5 or not. It's less than 2.5, should be so that is okay. Thank you. The next steps will be given to you and in the next video. Thank you.